Dear students, in the last class, we have discussed how to present a k-variable linear regression model in matrix form. In the present class, we discuss the assumptions of classical linear regression model in matrix form. We have discussed these assumptions earlier. Now we discuss the same assumptions using matrix notations. Let us see what are these assumptions. Assumption number 1. We have specified earlier that the first assumption is linear in parameters, linear regression model. That is why the dependent variable is a linear function of the parameters. Now, in matrix terms, we say that the vector of sample observations on Y may be expressed as a linear combination of observations on explanatory variables plus the disturbance vector. That is, the vector of observations on Y may be expressed as a linear combination of observations on explanatory variables plus a disturbance vector. That is, Y is equal to beta 1 x1 plus x2 plus xk plus u, where y is the vector y1, y2, yn, x1 is the vector of units, x2 is the vector of the variable x21, x22, x2n, and xk is xk1, xk2, etc. xkn. So, the vector of observations on Y can be expressed as a linear combination of observations on explanatory variables x plus the disturbance vector u. And more compactly, we write it as y is equal to x beta plus u. X beta plus u with the order y is equal to n by 1, x is equal to n by k, beta is equal to k by 1, u is equal to n by 1. That is the first assumption. Linear in linear regression model. The second assumption is expected u equal to a null vector. That means u is a vector. So, expected value of u is u1, u2, etc. un is equal to expected u1, expected u2, etc. expected un is equal to a null vector expected u equal to 0. That is expected u1, u2, expected un. So 0 and n by 1 vector of order n by 1, a null vector. In scalar terms, we write it as expected ui equal to 0. In scalar terms, we write it as expected ui equal to 0. The third assumption is in scalar terms, we have written the assumption of homoscedasticity as expected value of ui minus expected ui square equal to a constant sigma square, and expected value of ui minus expected ui into uj minus expected uj equal to 0. This is the assumption of homoscedasticity, and this is the assumption of no autocorrelation. In matrix terms, we write these two assumptions as expected u transpose is equal to sigma square I. Expected u transpose is equal to sigma square I. Now, in the last class, I have written expected value of x minus mu transpose as equal to the variance covariance matrix. Now, this specification is a special case of this. We know that expected u is 0, so expected u 0, so u here also 0, so x transpose u transpose. Now this can be expanded as expected value of what is u? U is u1, u2, etc. un, u1, u2, etc. un. So this is of order n by 1 by n. So the resulting product is a matrix expected value of u1 square, u1, u2, etc. u1, un. Then u2, u1, u2 square, etc. u2, un, etc. un, u1, un, u2, etc. un square. Taking expectations inside, you will get it as expected u1 square, expected u1, u2, etc. expected u1, un. Then expected u1, u2, expected u2 square, etc. expected u2, un. Similarly, expected un, u1, expected un, u2, expected un square. This is equal to expected u1 square sigma square, expected u1, u2 0, 0, 0, sigma square 0, 0, 0, sigma square, and can be written as equal to sigma square into 1, 0, 1. So this is equal to sigma square I. So expected u transpose is sigma square I, means homoscedasticity and no autocorrelation. these two assumptions are combined. And we write simply it as expected U transpose because expected U is 0. So actually, this is a special case of the variance covariance matrix in general form. And sigma square I, when the variables are pairwise uncorrelated and having same variance. And as I discussed earlier, this is the variance covariance matrix. The diagonal elements will give you variances and the off diagonal elements will give you covariances. And as I told you earlier, the variance covariance matrix is symmetric. Symmetric means if you interchange rows and columns, you will get the same matrix. So it is symmetric. As I told you earlier, it is positive definite also. Positive definite also. That is a terminology we will explain in a later class. So this is the third assumption in matrix form. Expected U transpose is equal to sigma square I. And remember this, we will use this expression later for the derivation of the properties of estimators. The fourth assumption is the X matrix is non-stochastic. The X matrix of order n by k. Our model is y is equal to x beta plus u, the PRF in stochastic form. So the X matrix has the order n by k and it is assumed to be non-stochastic. That means X is assumed to be fixed in repeated samples. X is assumed to be fixed in repeated samples. As I told you earlier, if Y is stochastic, there is no reason to believe that X is non-stochastic. So if Y is stochastic, X is also stochastic. There is no problem even if X is stochastic. The only requirement is that X is not correlated with U. But this is a simplification used in the introductory econometrics textbooks. If X is non-stochastic, then the assumption that covariance xi ui is equal to 0 is automatically satisfied. So that is the fourth assumption. So this is only a simplifying assumption for the easiness of derivation of sum of the results. The fifth assumption is in matrix form. The fifth assumption is the rank of x is equal to k. And this is a very important assumption. Let us see what is meant by this assumption. Consider a general k variable model. The X matrix is like this. A column of units x21, x22, x2n, x31, x32, etc. x3n. Then xk1, xk2, etc. xkn. This is the X matrix. The order of this matrix is n by k. That is n rows, k columns. And as I told you earlier, rank of any matrix X is less than or equal to minimum of m n. Less than or equal to minimum of n or n. Suppose that in the matrix X, all the rows and columns are linearly independent. If so, the rank of the matrix will be minimum of rows or columns. So when I say that rank of X is equal to K, it also means that n is greater than K. This was an assumption we have discussed earlier. Sample size must be greater than number of parameters to be estimated. Now, if you consider this X matrix, it is clear that it has K columns. Now, rank of X is equal to K means none of the, so we define what is known as column rank, and the matrix has K columns, and the rank will be equal to K if and only if all the columns are linearly independent. All the columns are linearly independent. Suppose that there is a relation like this: x3 is equal to 2x2. x3 is equal to 2x2. In that case, if x2 is 5, x3 becomes 10. If it is 10, 20. If it is 30, 60. 20, 10, 20. If it is 20, 40, like that. That means the third column is a multiple of the second column. That means column 2 and 3 will be linearly dependent because there is a dependency here. x3 is equal to 2x2, like that. So, the implication of this assumption is that there should be no multicollinearity. If there is no multicollinearity between explanatory variables, all the columns, that is each column representing one variable, each column will be linearly independent. And we define column rank, not row rank. And remember this always, row X is less than or equal to minimum of M or N. So, as we specify row X as equal to K, we assume that N is greater than K. Then only rank will be equal to K. And provided that N is greater than K, the second requirement is that all the columns are linearly independent. That means there will be no multicollinearity. There will be no multicollinearity. And as we have discussed earlier, no multicollinearity means there exists no set of numbers lambda 1, lambda 2, etc. lambda k, such that lambda 1 x1 plus lambda 2 x2 plus etc. lambda sk is equal to 0. If this condition is satisfied when lambda 1, lambda 2, etc. lambda k are not simultaneously equal to 0, there is perfect collinearity. So that one x can be written as a linear combination of other x. And if this is equal to 0, when lambda 1 is equal to lambda 2 is equal to etc. lambda k is equal to 0, there is no collinearity. And in using matrix and vectors, we write it as lambda transpose x equal to 0. Lambda transpose means lambda 1, lambda 2, lambda k, x, lambda transpose x, lambda 1, lambda 2, etc. lambda k, x, x1, x2, etc. xk. x1 is equal to 1 is equal to lambda 1 x1 plus lambda 2 x plus etc. is 0. 0. It is 0, not a null vector. So this assumption is very important. Rank of x is equal to k. And the importance of this assumption will be discussed later. rank of x must be k, otherwise we cannot find the values of estimators. That is the fifth assumption. Then the last assumption in matrix form is U is normal with 0 and sigma square. The vector U is normal with the mean vector, a null vector, and variance covariance matrix sigma square I. In the last class, we have seen how to read it. The variables in the vector U is distributed according to the multivariate normal law with the mean vector, a null vector, and variance covariance matrix sigma square I. Remember this? And in matrix form, always remember this. This is a special case of the variance covariance matrix sigma square I, only when the variables are pairwise uncorrelated and having same variance. And in matrix form, also remember this point very carefully. Rank of x is equal to k. It does not mean that rank of x will always be equal to k. This is an assumption. This is a requirement. We assume that rank of x is equal to k. Otherwise, matrix inversion will not be possible. And if matrix inversion is not possible, derivation of OLS estimators is not possible. So these are the assumptions of classical linear regression model in matrix form.